This PhysCast looks at a problem involving polarized light passing through polarizers. Pause the video and read the question carefully. Now that you've read the question, let's begin our solution with an interpret stage, which is essentially what I just described in my first description there, that this problem involves light that is already polarized. So we might want to think about what we mean by polarized light, and in particular it's asking about the transmission of that polarized light through two polarizers. In our develop stage, a diagram will be particularly useful here. Let's think of our light traveling off in that direction, and we're told it's initially vertically polarized, and that means that the electric field of the light, of the electromagnetic wave the light is, must be oscillating up and down vertically. That light, we're told, then travels through a polarizer. And so here's our polarizer, whose axis is at 16 degrees to the vertical. So we could draw the axis of that polarizer in, and we know that between that axis and the vertical is an angle of 16 degrees. And then, as the light continues on, it travels through a second polarizer here, whose axis orientation we're trying to figure out. We don't know what angle that particular polarizer is at. But what we do know is that if the initial intensity of this light is S0, then we know that the final intensity of the light must be 7% of that initial intensity. So it must be 0.07 of that S0. So what we'll need here is some information about how the orientation of a polarizer affects the transmission of polarized light through it. And either by looking through lecture notes or perhaps through the textbook, you might see the law of Malus here, which says that the intensity that passes through a polarizer is the initial intensity multiplied by the cosine squared of an angle, where this angle here is the angle between the electric field direction and the axis of the polarizer. So now, in our evaluation step, the first thing we can think of is the intensity of the light through the first polarizer. Let's call that intensity here S1, after the light has passed through that first polarizer. And we can see there straightforwardly that that intensity will be the initial intensity S0 multiplied by cosine squared of 16 degrees. Then the intensity that goes through the second polarizer will be the initial intensity falling upon it, which we're calling S1 here, times the cosine squared of theta, where theta is the angle now between that initial 16 degrees and whatever angle this second polarizer is going to be set at. And we can write that now, because we know what this S1 is. It's just S0 cosine squared 16 degrees times cosine squared of the angle that we don't know. And the question tells us this must be equal to 0.07 multiplied by the initial intensity. So we can rearrange that expression there, this expression here, relating things that we know and the one that we're looking for, to tell us that the cosine squared of this angle must be 0.07 divided by cosine squared of 16 degrees, or that the angle we're looking for here must be the inverse cosine of the square root of 0.07 divided by cosine of 16 degrees. And if you do that carefully in your calculator, you'll get an angle of 74 degrees. Now importantly, that's 74 degrees between the initial direction of this electric field, which is of course the same as the axis direction of that first polarizer, because the polarizer absorbs all of the electric field that's at right angles to it, and only transmits electric fields parallel to the axis. So the electric field of the light after the first polarizer is aligned with the axis of that first polarizer. And so this 74 degrees that we've just calculated is the angle between that 16 degree from the vertical direction and the axis of the second polarizer. So in fact there's two possibilities here. We could be 74 degrees clockwise from that 16 degrees or 74 degrees anti-clockwise, depending upon how you're looking at that polarizer. We can choose either one of those, so let's just choose that we're going to add that 74 degrees to the 16 degrees. So that says that the axis of the second polarizer will be 74 plus 16 degrees, which is actually 90 degrees to the vertical. And that's kind of interesting. That means in our diagram here, we should have drawn that axis out in this direction here, horizontal, and the angle theta was in fact the angle between 16 degrees and the horizontal, that's 74 degrees there. And that's worth some consideration in our assessment step here. This second polarizer has its axis perpendicular to the initial polarization direction. And if we simply had that initial light falling on that second polarizer, we'd expect no light to be transmitted. The transmitted intensity would be 0, because using Malis's law, cosine squared of 90 degrees gives us 0. So the light just falling on the second polarizer would be completely blocked. But this first polarizer actually changes the direction of that electric field. So it's important to understand that that first polarizer doesn't just absorb some of the electric field, which is what it does, but it actually has the effect of changing the orientation of that linear polarization of the light. So the first polarizer, in some sense, rotates the electric field.